In this video, I'll talk about the halogenation of alpha carbon under basic conditions, and sometimes you also call this haloform test. Not all the time, but sometimes haloform test or an iodoform test if you have a methyl ketone or an aldehyde. If you don't have a methyl aldehyde or a ketone, then it would not be running in an haloform test. That's one thing you want to make sure you're aware of. The difference really between under an acidic and basic condition is, suppose if I was running this reaction under acidic condition, and when you do this under acidic condition, you install this only once. So I'll ended up getting, let's say in the presence of an HCl here as an acid, I'll have an bromine installed at the alpha position. That was really the primary thing there. So this would have been your new bond here. Under basic condition, however, it has a potential to kind of go in there multiple times and it would remove all the protons. So technically speaking, I have two hydrogen atoms right now on this alpha position. So I can go ahead and remove both of them and eventually I'll install bromines on both of them. Obviously, you're not doing it together, you're doing it in steps, but that's really the downside of it. So the question would be, what if you just want to install it once? Then you don't really want to use the bromination or halogenation under basic condition, but rather you will use this under acidic condition. Now, if you had another proton here, like right now, I only had two hydrogens, so replaced only two hydrogens and replaced those with bromine. But if you had another one, it would replace that one as well. And that's when you eventually kind of go on to do an haloform test. And that would happen only if you have a methyl ketone or methyl aldehyde. So I'll talk about that in a minute. But let's just kind of talk about the mechanism, why this actually really do that. So if I want to start out in terms of drying the mechanism, the first step here would obviously be the deprotonation of that hydrogen. So I'm going to go ahead and remove that proton from here, that carbon, make the enolate out of it. And when I make the enolate, so I'm not going to draw the hydrogens there. I got an oxygen here with a negative charge, got a double bond here. And certainly I can go ahead and draw the resonance of that. And a lot of time, once you get in a hang of it, you may not be seeing the resonance being drawn over and over. But in the beginning, it's a good idea to kind of know that, okay, I got the resonances of that. So I get a negative charge here. So that's the enolate. So this is an ambident nucleophile because you have an oxygen that has a negative charge that can potentially act as a nucleophile. And you also have a carbon that can potentially act as a nucleophile. Now, between the oxygen and carbon, carbon being less electronegative, it's more likely to act as an nucleophile. So that's why a lot of time you would see the carbon acting as an nucleophile in these reactions. So the next step, I would have the bromine installed on here. So I'll use this lone pair to tack on the bromine, and then the other bromide leaves. So you ended up making a bromine there. So I'm going to go ahead and draw the bromine here. But then remember, there's already another hydrogen that we just didn't draw both of them, but we only removed one of them. So there's still one more hydrogen in there. And your side product here is obviously the Br minus. So what happens once you install the first bromine, and especially when you're doing this under basic condition, this proton actually becomes even more acidic now. Why it's becoming even more acidic compared to the proton when you were up here is because of the electronegativity factor of the bromine is going to help stabilize the conjugate base that's going to be made after losing this proton. Now, in the previous case, you didn't have that bromine there. So yes, the pKa of, probably would have been like 18 or 19 for this aldehyde. But now, as soon as you install the bromine, that's going to have an inductive effect and make that conjugate base even more stable. So as a result, that means this proton is going to be even more acidic. So that's the downside of running these halogenations under basic conditions. That's because once the first halogen is installed, it makes it a lot easier for the next set of hydrogens to leave because they become more acidic in that case. I'm going to go ahead and remove this proton here, get an enol here. So I'm not going to draw make the enolate here. I'm not going to draw the resonance. So I'll just go ahead and get a negative charge on here. But if you do want to draw the resonance, I'm just going to go and draw that here. This comes down here and that comes out here. So we get a double bond here and a negative charge here. So again, now in the next step, I want to go ahead and use second set of bromine here. So your second set of bromine would technically have this lone pair on that carbon kind of attacking that bromine. You can also show it from here. That's one way of showing it. If you don't want to draw both of the resonances and draw only this resonance, you can show it from here. But for the most part, you always go with drawing the most stable resonance. So this one is in a more stable resonance. So you may be drawing this one and the mechanism and not even drawing that one. So if you're drawing this one, then how does the attack kind of takes place? You can show that. Okay, this is going to go back and reform the pi bond here, and then this pi bond is going to be used to attack the bromine. So either one of those ways, when you're showing them, it's fine. But for the most part, you will be showing the second resonance structure that I have drawn here as your major or stable resonance. So it would be shown in the mechanisms as well. So let's go ahead and get this double bond formed here. And now I got a new bond formed and I got the bromine installed and you have the Br minus again. So it would kind of stop right here. That's because I don't really have any other hydrogen to be removed. So if I have another hydrogen, then I would go ahead and remove that as well. So I will just kind of stop it right there and that would be your major product in that case. But now let's suppose if we had actually three hydrogens, then what would happen? So suppose I'm, you know, using this situation here where I do have two alpha positions. I got one on the left side, one on the right side, but one on the left side does not really have any protons. It's only the one on the right side that has the protons. And it turns out actually has three protons. So I'm not going to show the mechanism because the mechanism is going to be kind of the same as what we've done up here. But in this time, you're going to be going in there three times. So you install, like if I go ahead and show the first step here, you remove the first proton to make the enolate here. So I got the enolate formed, and then in the second step, I can have this iodine kind of coming in into the play. So this falls back, and this pi bond would be used to grab onto that iodine. Okay, so now I have one iodine installed. So as soon as you have the first one installed, it makes these hydrogens even more acidic, and it would be easier to remove the second hydrogen in this case. And that's exactly what happens. You run this again with an OH minus because you still have that in the solution with an I2. And after a few steps, making the enolate and all that, you would have the second one installed. So I don't want to show all those steps again, but you kind of get an idea that you just kind of redoing it. So you got the second one installed, And now that makes this proton even more acidic because now you got the inductive effect coming from two iodines here, or two halogens. So then in the next step again, you have next couple of steps, you do that again where the OH minus will remove that proton, and then the I2 comes again and get installed on the third one. Now, once you have three iodines installed, or in matter of fact, three halogens installed, that could be like, bromines and chlorines as well, that makes this a really good leaving group just because of that all that inductive effect. Now, that wasn't really the case when you have two halogens installed. Like once you have two halogens installed, like we saw in the previous case, and I don't really have any place to replace the or install the third halogen, it kind of gets stuck in here and it doesn't really go anywhere, and that would be your final product. But if you are installing three halogens like we did in this particular case, that makes this set a really good leaving group. So this is where the reaction kind of differs at this point, where I can have an OH minus coming in again, acting as an nucleophile, and it's going to go ahead and attack this carbonyl carbon, and this is going to come out. So the pi bond is broken. You make this tetrahedral intermediate here. So let me go ahead and redraw that. So I got the O minus here, and I got this tetrahedral intermediate with an OH here momentarily. Now, like I said, it's gotten a good leaving group, so I'm gonna go ahead and reform that pi bond. So when I go ahead and reform that pi bond, this is gonna go ahead and get kicked out because that's in a good leaving group. So now I'm in the process of making like a carboxylic acid here. So let me just kind of redraw the whole thing here at this point. So I'm going to go ahead and reform pi bond, and I got the OH here. So remember, I'm about to make an acid under basic condition, which is not going to happen. So we make this, and then your leaving group would have been Ci3 with a negative charge on that carbon. Now that's at a base, and you have an OH minus anyways in the solution, so I'm not going to be leaving this in the protonated form because that's in an acid. So that Ci minus 3 is going to come in and grab that proton and create a carboxylate here. So your final product really here would be a carboxylate. So you created a carboxylate ion, and you create it with one less carbon. So if you look on the starting material where you have a carbon here, and that was really a methyl ketone. And that's what we said, like the Haloform test would be run when you have a methyl ketone or a methyl aldehyde. And you lose this carbon. So the carboxylate you make here is actually going to be one less carbon. That's because that carbon is gone on to make that haloform here. In this particular case, it would make CHI3, which would be called an iodoform. Now, this iodoform is actually going to be in a solid and is going to precipitate out in the solution. And that's how you know that the test is positive once you see the precipitates being formed. And the precipitates is usually coming from the haloform, and in this particular case, the iodoform. And that would only happen when you have an methyl ketone. So a lot of time, this halogenation under basic condition is used to test whether or not you have a methyl aldehyde or a methyl ketone in a particular case. There's only one methyl aldehyde if you think about it. Only one methyl aldehyde would be just an acetaldehyde, because you have to have a hydrogen on that side. But as far as the ketones go, you can have like, so many different types of ketones that can have a methyl on one side and any other R group on the other side. But there's only one methyl aldehyde that you really have to worry about that would give positive iodoform or haloform test.